What's that?
I said that's cool before realizing that I've probably seen microphones before in my life.
Yeah, they're still pretty cool. They're still pretty cool, though, you know?
Yeah, I think it's pretty cool.
It's kind of magical, wireless technology, even though it's everywhere. So if you wanted to, you could put your laptop maybe over here or wherever you like.
Is it on already?
It's on, yeah.
Oh, whoops. I shouldn't talk into it then.
Hey, there you go. Nice. Great. Okay, you got this piece over here. Great. You want to set my laptop up? Can you put this piece over too? We can film everybody's too if they want. We can film everybody else's too if they want.
Let's see if they want it. Yeah.
No audio.
Nope.
Also, we can do just raw HDMI.
Yeah.
You know what? I'm going to leave this here just in case.
Someone else
Yeah,
can
but
do it.
let's
Other laptops are.
for sure. But let's just.
Would you prefer to
I
go straight
prefer.
up?
You can leave it here.
will.
We're just gonna go raw.
There you
Yep.
go.
Great.
All right.
Wow.
Beautiful. Thank you very much.
Too close to that.
I'll get very intimate with. Oops.
You all good?
No, I was making a joke, not knowing that everyone would hear it. That's okay. My jokes are funny.
Fine. How are we doing on time? It's time to start, right?
Yeah.
Oops. I'm gonna pass this off to Peter. Peter? Yep. You are, sir? Alright. You want to start us off?
Sure, yeah.
Just give me a second here to. You want to dox myself on the on the screen here? Is there anything special you have to do? You just plug it in, right?
I just plugged it in.
There we go. Great. There we go. Absolutely. Yep.
All right, everyone, let's get started. Thanks for coming to this last lecture of 858. So today we have three final project presentations for you guys from three different groups that did something other than the default encrypted file system project. So first off is Joseph and Michael.
All right, hey everybody. My name is Joseph,
I'm Michael.
and today we're going to talk about what we call Lord of the IOU rings. So what is that? To start, what's an ODay? So who here knows what an ODay is? Hopefully a lot of people. Good. So an ODay is a brand new vulnerability in a piece of software that nobody knows about. So we are the first people to know about it. The developers have had 0 days to mitigate it. And yeah, that leads into our next point, which is we're also going to be doing a case study of state-of-the-art operating system fuzzing tools. And so with that case study, the case that we're going to be studying is a brand new, never before announced Linux kernel ODay and exploit that we're going to be sharing today.
So CVEs are typically pretty hard to find. In 2021, there were only 159 of them. And only 11 of them actually led to code execution. And Google will actually pay you up to $90,000 if you can run an exploit on their servers and escape and read one of their flags. So we didn't manage to do this, but we did get awarded a CVE with a base score of 7.8, which is decent. And we got recognized by Red Hat, SecAlerts, Debian, and Ubuntu for it. That's our names up there. So this talk, in case it wasn't clear, so this talk is about how we actually did this exploit and kind of our process behind it. So this is our timeline. So as you can see, we started fuzzing in early March. Took us, and one thing I want to point out here is it took us almost a month from the first crash to actually isolate the bug, patch it, and figure out what was going on. We had a small scare there. That's Joseph carrying me being sad. And 3 days later, we achieved local privilege escalation and were awarded a CVE. So, going to start off with the fuzzer. So, we used a fuzzer called syscaller, which is a fuzzer by Google, commonly used for fuzzing kernels. We had 12 different types of crashes, and you'll notice 145 of them were in these two functions, biopol and IOC bio-IOpol. So those are the ones we focused on. And what syscaller does is it actually gives you a reproducer. This might be hard to see, but hopefully you can tell that even if it were in high resolution, you still have no idea what was going on. There's just so many things that are being allocated. Most of them are useless. So one of our first steps one was understanding it, which as you'll see later is kind of a mistake, but another one was actually minimizing it. So we went from that big blob to just this little snippet. And so this was really helpful because we could run this, kind of debug it, and we didn't have all this extra noise to deal with. So syscaller has a bunch of different crashes. The one we were focused on was a use after free. So that's what we thought was going on. And we had a lot of reasons for this. One is that syscaller literally told us it was a use after free. And there are quite a few traces that only appear when it's a use after free. So for example, here it tells you exactly what's being used and when it's freed. And so at this point, we were quite confident it was a use after free. We isolated the commit to find which commit in the Linux kernel actually introduced this bug. And so here, I was very confident it was a use after free. And one thing I want to emphasize is I spent weeks here staring at the source code trying to figure out why a use after free was occurring. And what would have been way better is if instead of coming in with the presupposition that syscaller was right, if I had actually just run things kind of myself and tried to figure out what was going on. So here, Joseph's going to talk about how he figured out it actually was not a use after free and how he exploited it from there.
All right, so let's take a look and see a little bit closer where that crash is happening. So this is the method that the crash occurs in. And if you look right here, this read is where the issue comes from. So when we try to dereference this bio object, we have a crash. So the name of the game is what's wrong with the bio, who's corrupting it, and when does it happen? And so the bio object in this function comes from this IO kernel IO callback object that's part of the IO U-ring subsystem. This read-write object KIOCB. Private field is where bio gets inherited from. So the name of the game is figure out what's going on with this. And so to start, we began with what's called ftrace, which is a Linux function tracing utility. And we told it, hey, give me everything from the IO U-ring system. We ran the exploit. We looked at what was happening. And if you'll notice, we have this asynchronous worker thread. So our main exploit 72 process is running, constantly calling this IO U-ring release. We have this asynchronous worker thread pick it up. It calls the request cache is free, and then you'll notice we use the object right afterwards. So that's your quintessential use after free, right? Like it looks like it's a use after free. And so what you'll notice is that immediately after that free happens, the bio object is corrupted. The private field is now some other value, and that is a little bit strange. It shouldn't happen so fast. So what's actually happening? So why is bio getting corrupted so fast? So let's do a little experiment to figure out what's going on. So we're going to start by disabling ksan. Ksan is the address sanitizer that kind of tells you what's happening. Problem with Ksan is it stops your code really early if it detects an issue. We want to kind of see how far we get. So let's turn off Ksan, but we're going to turn on something called the slub debugger. Slub is this how the kernel heap works, and the slub debugger helps you figure out what's going on in the heap. We're going to patch the allocation of these objects. So we'll talk about this in a minute, but when these things get allocated, they get allocated in bulk. So we're going to turn off the bulk allocation and just allocate one. And the reason we're doing that is because it forces a free every time it gets reduced, and then it's also a lot easier to trace. And so we're going to use GDB to watch that private field and just see what happens. And so the slub debugger gives us some information. Basically, the two things to look at here are use after free or uninitialized memory. It'll tell you what's going on. And so we're going to start with setting a breakpoint in this request refill object method. This is where we get our objects from. You'll see we start there. And then this is very interesting. So if you notice in the crash log, there's a bunch of errors that say SCSI error handler is freaking out. So the SCSI is the block device that we're talking to. And SCSI starts having all these errors. And then one of the things these error does is it sets this block device end IO, nulls out the private field. And then immediately after, the request cache free sets it to this we've just freed it because we're the slub debugger. We're going to tell you we just freed it. And we repeat the cycle. And since we're running on a minimal busybox installation, we just get the same object over and over again, and this loop just keeps happening. So why is it not detecting uninitialized memory? Well, if you look inside of the request refill, there's actually this short circuit path where you can actually skip going back to the allocator and just give you something back from the free list. So what's happening is we're actually recycling these IO request callbacks and never really freeing them. So we have this big linked list of freed ones, and the IO U-ring system just reuses them to save a trip to the allocator. And so what's happening is if you look a little bit closer here, I've kind of misled you in this screenshot. If we really freed, you would see it in this trace. ftrace would tell you, hey, I just called kmem free. We never actually call free. We go into that short circuit path and keep it in this freed list. And so what's happening is that ksan and syscaller are getting confused by the fact that we recycle objects. And so we're thinking the IOK IOCVs are being used after freed, which isn't true. And so to test that hypothesis, we added some print case, which printf debugging is the way to go, always. And so you see that we actually do some allocations, we trace the pointers through here, and we actually get a crash on an object that has only once been allocated, never been freed, never been touched by anything else in the system. That's kind of weird. And so we just crash on this brand new object, never freed, just allocated. And so if you look deeper into some of the crashes, some of the use after frees are actually in these other caches. Like you can see here, we have a file cache that has nothing to do with what we're doing. And so why are we seeing all these different objects inside of this one space? Let's find out. So I ran it a whole bunch of times just trying to see what was going on, and we hit what I call the magic crash. And so this crash is kind of the cornerstone for the rest of our talk, but basically what we saw, if you look closely, it's a wild memory access in this particular address. And now the CTF players among you might recognize these bytes to be ASCII. If you look, this actually, skipped ahead a little bit. You'll notice this spells out some string. So some string, which we trace back to a socket packet, was being put inside this object. So it is possible to actually overwrite this field by some string data, right? So I texted Michael at midnight, and I said, I have horrible news. I patched the bug. It does not seem easily exploitable. Sad face.
No.
And so, yeah, we did patch the bug. It was uninitialized memory. And what happened is we found out that these bugs that we saw earlier, all those 141 crashes in that subsystem, they're all the same bug. And so that patch, all these crashes just go away. All the different reproducers, it was all the same bug. But syscaller didn't say that. Syscaller said it's 12 different bugs in these areas, these all sorts of different things going on, nowhere even close to right. So let's go back to that thing I said to Michael. Why is that horrible news? We patched the bug, right? Well, what happens in the Linux kernel is you have these caches where this is a slab cache where the IO object is in its own cache. When you create a new one, they are all there's a whole bunch of them ready to go, basically. And so when you want to have a new one, the next one comes right from this cache. Now, the important thing to note here is that only IOK IOCVs go in that spot. We can't allocate anything but IOK IOCVs in this cache. We can't race it. We can't put our own object there and then free it and hope it gets picked up. So we're a little bit out of luck here, right? Not exactly. So go back to this crash. We did see that it's possible to put some data from some completely unrelated object into the system. It happened. So how do we make that happen reliably? Well, you'll notice that, again, allocations happen in bulk. So what if, instead of trying to race in the slab cache, we did something a little bit different? So let's fill as many pages as possible with pointers to some object, and we'll talk about where that object is in a second. We're going to free them all at the exact same time to return all these pages at once to the buddy allocator, and then we're going to trigger our bulk allocation. And so since we just triggered a bulk allocation and there was no page there before, it's going to grab a new page from the buddy allocator and hopefully pick up one that we just put there. And so there's a couple different ways to do this. We looked at two of them, and I'm going to skip the user fault FD one for now for time, but here's the idea. So whenever you're doing a heap spray, what you want to do, at least our approach, is you spray a bunch of objects into some random cache, we don't care where, and then we free the page, pass it back to the buddy allocator, and then the next thing that runs will pick that page up as its new page. And so this is how we're going to get our data into that uninitialized field. And so I'm going to go ahead and skip this, but basically we tried this and it didn't work. So overhead was really high. That's the TLDR. So what we ended up working was we used this message send API where we can send inter-process communication messages. And then this message send thing lets you allocate an object in the kernel. So we spawn a bunch of workers. Each one of them just spams message send over and over and over again. And then they all wait. So they're all done to minimize any fragmentation or self-contention. And then we free them all at the same time. So a whole bunch of pages get shipped right back to the buddy allocator. And then we can immediately ask for a new page for the other cache. And so that works. We can control the private field. How do we go from here? What do we do next? So this crash that we were seeing before, remember it was this bio poll method. And if you look very carefully, there is actually a code pointer that's dereferenced from the object that was pointed to. So all we have to do is find a way to pass all these checks up here, get down to that gendisk method, and have it dereference the virtual function table where we can run our payload. And long story short, we can do that. So again, this is that dereference right there. So here's how we're going to do it. We're going to go to user space. There's two different approaches you could take here. If you had a KASLR leak, you could do this all in the kernel heap. We're going to just do it in user space to save time. So in user space, we're going to set up a fake object, points to this fake block device, fake request queue, fake gendisk, and lastly, the fake virtual function table. Only the appropriate methods are filled in here, just what's needed to pass those checks. And then we're going to spray pointers to user space inside of the kernel so that those objects get picked up. Now, the reason we have to go to user space, again, is because we don't have a kernel address space leak. We need to know where the address is, so we're going to put it in user space. And so that brings us into our requirements for this exploit to work. You need to have SMAP and SMEP disabled. So these features are two features that basically say, hey, I'm the kernel. I won't ever access or execute user space memory. You need those features off. One thing that we did notice is that IOU ring is accessible from the Android sandbox. And this SMAP and SMEP might not be supported on every Android device. So there might be some exploit surface there. We didn't really look into it.
We also needed a block device. And in this case, we chose to use SR0, which is just the SCSI disk drive.
And so let's go back to that magic crash then. The astute viewers among you might have noticed that the crash all comes from this one system call, exit group, which is a little bit of a bummer because that means that as soon as our code exploit runs, we can run our payload, but then we lose the process. So the crash happens right as we're about to quit. What can we do? Well, instead, what we're going to do is go to the parent process. So this is how our payload works. To be honest, I'm not super familiar with Linux payloads. This is just one we wrote. This could be standard. This could be new. I don't really know. But the idea is we're going to load from the process, like the per CPU task structure that's in the GS segment. At a constant offset there is the current task, so you don't have to get an address leak. You load that in, you find the parent task, and then you just clear out its credential struct. And then we're going to return a -1 because this is still a fake IO poll method running. We're going to say, hey, our fake block device didn't succeed. So that'll just get the kernel to stop asking us. And so, without further ado, let's actually take a look at it. So, go ahead and push this over here. Just a little bit of a spoiler there. All right, so here we are inside of just my server, and I'm going to go ahead and launch. Go ahead and launch a new Linux VM, and this is just running in QEMU. And so we're in a BusyBox install. We can say ID. So you can see I'm just jravi. Who am I? Just Linux, right? All right, so let's go ahead and do our spray. You'll notice I have added some print case here so you guys can see what's happening. But we're spraying into the kernel, flooding those pages, and now we're going to free them all. And now we're going to go ahead and run the exploit. And you'll notice that my name has changed. Suddenly I am root. So it works. Thank you. And so we did upstream our patch. This was upstreamed a couple weeks ago. We got accepted, and all we had to do was just one line change, null that private variable. That's all you need to do. And so we're upstreamed and backported. So for those of you on 5.17, you are all good. Those of you on CSAIL Ubuntu, not so much. And we did get the CVE as well.
So we tested this on a couple things. So we tested it on Docker, which is kind of cool. So it means if you're running in a container, you can compromise the host. QEMU, as you just saw. And we also tested this on Ubuntu 2004, the most recent Ubuntu in VMware. Wasn't brave enough to test it on my actual computer. So there are a couple of takeaways here that we think we can kind of take forward. One is that the kernel is so big that it was really hard to kind of target our fuzzer. So it would have been really nice if we were able to kind of target the IOU ring subsystem more. So there's probably still tons of kernel bugs out there. So, if you want to run a fuzzer, go for it. And so this is kind of one thing that bit us a little bit. Spent a ton of time on static analysis, but really some of the most useful things were honestly, the printf statements up there. I feel no shame on doing that. And so another thing that I really want to emphasize is that a big misconception I had coming into this first kernel exploit at all, I thought the fuzzer would take care of so much more of it. But once we found the bug, it was like a month of just straight. It was so hard to find what was going on. So one of this was just the reproducer wasn't super hard to read. And I think there's honestly a lot they can do there, just engineering-wise, to make it more readable. Targeting fuzzing is hard, but kind of the biggest takeaway is that fuzzers just give such a small portion of the work that actually needs to be done. So I think it'd be really interesting to kind of see is there a way that we can actually improve the output to actually help our analysis a bit more, hopefully without killing performance.
And yeah, we're going to post a blog post at this link if you want to read more about it. This will have everything, including the crashes and the exploit. It's not up yet, though, so stay tuned. That's it. Thank you. Yeah, so the question was, how does the fuzzer work? What is the fuzzer doing? So what the fuzzer does is it takes what's called a corpus of system calls, and it says, open will give you a file descriptor, read takes a file descriptor. And so it mixes and matches these system calls so that the types match and creates these interesting cases. That's kind of the idea. But you can also imagine cat dev random into the kernel. Anything else? Yeah. Yeah, so the question was, did we know we would find a kernel bug before we did this? The answer is absolutely not. So when I set out to do this, I basically said, I'm getting a CV in Linux or I'm failing the project. That was what I did, and not getting a CV wasn't an option. So we just fuzzed really hard and then spent a lot of time on it.
And I was like, that sounds great.
We warned these guys this is like a high-risk project, but they somehow stuck with it. So it's impressive that they found the bug.
Yeah, this is the stupidest project I've ever done in my life. Just saying.
All right, thanks very much. Great.
All right, that was really cool. But today our team is going to talk about a homemade U2F device that we made. So let me introduce myself. My name is Ashika.
I'm Tork.
And I'm Abdullah.
And then together we made a U2F Teensy authenticator. So first thing I want to talk about is the FIDO Alliance. They've just come up in the news recently for a bunch of big companies like Apple, Microsoft, and Google are starting to ramp up support for FIDO. And what FIDO essentially is like their entire goal is for a passwordless future. So log in with your phone or log in with a security key. But we're specifically focusing on the U2F, the FIDO U2F protocol. So with that, there's two different flows. This is the stuff we read in the paper. So there's two different flows, registration and authentication. And then there's three different parties. So we have the relaying party, which is our server, essentially bank.com. We have the client, which is your browser Chrome, so like me as a user accessing bank.com. And then we have our U2F device, which is this cute little, I don't know where it is. It's plugged in, okay. And we have our cute little U2F device, which we made with a Teensy. So I'm just going to quickly recap this, even though hopefully we should all know it. Essentially, the relying party is sending a challenge to the client. The client verifies a couple things. Client sends that to the token, U2F device. It comes back. Then the relying party wants to check whether the challenge is correct. And also check whether it was signed properly by the U2F token, and it saves the key from the U2F token, and then that's used later, again, for authentication. Similar flow, you send over a challenge along with some other information, make sure the signature is correct. There's an additional thing with a counter to mitigate from device duplication attacks, or device duplication, I forgot the word. And then you set the user as logged in. So we're going to do a little demo of our security key on GitHub.
Yeah, so for the past week, we've been using it as an authentication token to log into GitHub. And by the way, this is the repository. Sorry. Okay, so over here, I have a GitHub page. I'm going to try to log in and click use security key. And then the moment I provide user presence, it logs in successfully. Cool. So for our hardware, we chose to use I'm going to unplug it. Oops. For our hardware, we chose to use a Teensy 3.2 for multiple reasons. The first reason is it has an EEPROM on it, which means it has persistent storage when it turns off, so we could store something like the counter to prevent device cloning attacks. It also has full-speed HID communication, which means it could send 64 bytes per packet, and it's all fixed width. So it makes it easy to implement on cheap hardware, which is what the FIDO Alliance stands for. It's also small, fast, and it has accessible solder pads, so we can attach a male USB port to it. So this TNZI actually has a full-size male USB and a female micro USB port on it. So we use raw HID to communicate. So I think a lot of people are familiar with serial communication. That's the thing you communicate with an Arduino and you plug it into the Arduino IDE. We use HID, which is a transfer method that has smaller data chunks per transaction, so it's easier to implement in hardware again. It has no drivers required, so it's like plug and play. You plug it into your browser without having to install an application or drivers before, so it works. It has fixed latency and overhead, which makes it also again easier to implement in hardware. And it has custom headers that are modified for the U2F protocol specifically. And we're specifically implementing the FIDO2 U2F HID protocol. So there's two protocols over here: the U2F HID, which is the HID communication protocol that U2F uses, and then U2F is the protocol that we're applying inside U2F HID. So as I kind of hinted right now, there's 3 layers of messaging that happens. The first layer is HID communication. So once you plug in your security key, we begin the HID protocol, and this usually sends out some values to the computer so that it knows, the client, so that it knows what kind of device it is. So the first handshake actually contains the usage page and usage ID, and that tells the application what kind of device it is. So there's authenticators like we're implementing, but there's also storage devices and phones. So how does the browser know that your device is actually a key and it sends requests to it is by setting the usage page to 0x FIDO, and that's how it knows to connect to it. And then it sends things like the vendor ID, and that's how you stop an entire vendor from logging in. So if you have a company, you can make it only work on your specific vendor IDs to log in. And there's other HID report descriptors that help the HID application know what kind of communication is happening. And then after that, the browser needs authenticating. So it sends out an HID command, and the HID command contains a high-level instruction of what the HID message should contain. In this case, it could be initializing HID communication that will cause channel allocation. So one thing that's important in this protocol is concurrency. You want to be able to plug multiple U2F devices and also have multiple clients access that U2F device. So managing concurrency with multiple channels is pretty important. It also can contain message type, which will contain payloads and some HID level errors, like hardware errors, not protocol errors. And within that, we have the application processing data unit, which contains things more specific to the U2F HID implementation rather than just general HID. So that would contain the channel number, so that to manage concurrency again. And then there's 2 types of APDU packets. There's initialization packets and continuation packets. They're very similar. The only difference is because we have fixed length buffers, sometimes you have to overflow that. So you send a continuation packet which contains less parameters and just identifies it's a continuation packet. Along with the channel ID, we send an instruction, which is, in our simple case, registration and authentication, but there's other vendor-defined functions that you can implement. And then there's parameters which help the protocol instructions operate. And we have the payload itself, and the payload would contain the request and response packets. So I'm going to hand it off to Abdullah.
Okay, so I'm going to talk about how the security key actually processes the payloads. During registration, the payload consists of 2 parameters, the application and the challenge. So the application is basically a hash of the origin, so it's unique to every origin, while the challenge is a random number, and it's basically used to protect against replay attacks. So the security key gets both of these numbers during registration and generates a public key and a private key pair, unique to that application parameter. It sends back that public key along with its certificate to the browser, and you can basically use the private key to authenticate the user by signing messages. But we run into the problem of actually saving the private key. If we store the private key on the USB security key, we're going to have to store a unique key for every application. We're going to run out of memory very quickly. So how FIDO solves that problem is that they basically encrypt the private key into a handle so that it can be reversed later on by the security key and sends that handle along with the public key and the certificate back to the relying party. So it's the relying party's job to store our private key in encrypted form. Now, during authentication, the relying party, that's the red part, sends the request message. It has the same application parameter and a different challenge, but it also sends the handle this time. Now, the security key basically can retrieve the private key stored in that handle and does the standard feeder UDF stuff by incrementing the counter, checking for user presence, and sends the counter and the signature back. Now, that signature is a signature of all the stateful information during authentication, which is the application parameter, the user presence bit, the counter, and the challenge. And the relying party can authenticate using the public key that this signature was actually signed using the private key. And that way we can authenticate the user.
Cool. So when are we going to see this in a lot more websites? So like GitHub had it there as an example. But essentially the bridge between the browser and all of these like U2F devices and security keys is this widely used API called WebAuthn. So essentially what it does is it's a simple API where you can load up all of the information that the relying party needs to send over into like this really simple JSON format, and then just ship it over and request some security key or some other WebAuthn device to like sign it and do all of the stuff there. So essentially it just allows the relying party to easily set parameters. And it's being used, or it's like being adopted by many different browsers. So like Chrome, Safari, Firefox, like it's becoming more and more widely like readily available. So I just want to go over, I guess, the relying party side. So it has a couple of steps that it needs to do. First, it is in charge of generating the challenge and setting like app ID information. So along with doing that, on the this is the registration side, so it's in charge of those two steps. It waits for the token to sign everything and make sure it signs the challenge and like gives all the other data as well. And all of the checking stuff happens on the relying party side. So we check the signature, and then we also store the public key and handle, as Abdullah said earlier. So for authentication, similar thing. You first look up the handle associated with the current user, send that over, get it back from WebAuthn, and then you want to check the signature using the public key that you saved previously. And also you want to check whether the counter increased in value since the last time you authenticated. And then, yeah, you can set the user to logged in. So now we want to show all the steps.
Yeah, so we actually made our own website to test this, but we're going to test it on an industry standard authentication device tester, which is made by Ubico. Yeah, so now I'm going to plug in the device. And I'll just walk through the protocol. If I start registration and choose a USB key, and now I could provide user presence by clicking the button and allow. And we registered the key, and we could see the technical details over here. We could see what the browser sent the authenticator, then the response from the authenticator, and then again what the relying party returned. And we could verify that the key is working, but like that. Then we could start authenticating, and same procedure, except this time we don't have to choose USB key because we're awaiting a response. And then we click, and authentication is successful. And same thing, we could verify that the browser to authenticator and all the responses are correct. Yeah, that's it. Thanks. Yeah, the USB communication itself is not encrypted. It uses HID, which is like very lightweight, so that we don't have to add any other packages that have to do pre-processing on the HID, just because we want it to be really cheap to implement. Everything else is like stored in an encrypted fashion, so there's some level of protection, but we do assume that the communication key, the security key, and the device are both safe.
All right, last up, Raymond.
All right. Hi, everyone. My name is Raymond, and for my project, I worked on Spark WebAssembly UDFs. So for anyone who's not familiar, Spark is a platform for big data analytics. So it works sort of similar to MapReduce. If you've taken the distributed systems class, you go over that, how Spark works. But basically, it exposes a SQL-like interface, and you can write SQL queries, and you can get previews of your data, and you can run analytics on it. It's a really cool platform. And I had experience with it over my summer internships, where we wanted to provide a platform for users to write their own SQL-like queries and process their data, but we provided the infrastructure. And the issue you run is really quickly is, well, how can we trust that the user queries are safe? So Spark allows you to write arbitrary user-defined functions. And user-defined functions can just be Java code, or they can be Python code. Any of the languages that Spark directly supports, they let you write user-defined functions, and that's really useful because you can call out to packages, you can use whatever libraries you want, and if what you're trying to get out of your data isn't easily represented by a SQL query, you can just write Java code. The problem is if we want to allow users to write arbitrary code and then we run it on shared infrastructure, we're now suddenly exposing ourselves to a lot of vulnerabilities. So as an example, the way that Spark does its execution is by writing temporary files. And you can have multiple Spark jobs running on the same hardware. And it's possible for one job to read the temporary files of another job that's on the same hardware. So at my internship, the way that they handled this issue was that every single Spark job ran in a whole separate virtual process, a virtual machine, its own environment. It was very custom, and the biggest issue, and was a huge problem for the customers, was that it took on the order of 30 to 40 minutes to spin up that whole Spark environment because it had to allocate new hardware, and it had to solve a Conda environment, and it had to download whatever the dependencies were. It was a big mess, and oftentimes the functions that users were writing were actually pretty simple, and most of the time was spent just setting up the infrastructure to run it securely. So the question was, how can we safely run the arbitrary user code without using this heavy VM? And the answer is to use WebAssembly. So we learned about WebAssembly, and it's also the subject of my thesis. So I've been spending a lot of time working with WebAssembly and all the different can of worms that you open when you explore it. But it's actually really, really cool. So if you don't remember, it's a compilation target for any language, any LLVM language. Actually, you can target WebAssembly. Commonly, you can use C or you can use Rust, but they're currently expanding the number of languages, and the topic of my thesis actually is WebAssembly for Julia. So maybe someday in the future you can write a Julia program and run it in WebAssembly. Now, WebAssembly can run your program in a web browser that's like the original design. So an example that you may have used before is if you go onto a chess website like Lichess and run the chess engine, it'll run a WebAssembly version of the chess engine on the analysis board, which is super cool. But you can also run WebAssembly programs in a runtime, like one called Wasmer, and that's what I used for my solution. So the plan of the attack was we'll take a user-provided untrusted program in C, and I'm going to compile it as a WASM module for them. I can do the compilation on my end. And then what I'm going to do is I'm going to serialize that module and pass it along to Spark. This is actually one of the more challenging parts because Spark requires everything to be serialized in a very specific format that Spark and Java are happy about. So just because something is technically serializable doesn't mean that Spark will accept it. So I had to do a little bit of finagling to get the module in a format that Spark would accept. And then the last step is just execute that WebAssembly module as some arbitrary map or filter function. So map function just take as input some content in a row and then output a new column. And then filter function, would be a Boolean and either include or exclude certain rows. So this is a little picture of the architecture that I implemented. So I wrote a front end in React that just lets you write some code and select the columns. I wrote a back end in Flask that takes the user code, compiles it, saves it into a space on my machine, or my server, and then a Spark executor that loads the WebAssembly module, does all the things that Wasmer needs you to do to initialize it, serializes it, passes it over to Spark, and then Spark executes it and then outputs the data. So one of the more challenging parts of implementing, which I kind of wanted to highlight here, was exactly the finagling of getting the WASM module as a UDF. So this is what the Spark code actually looks like. And you can see right here at the top, I'm passing in the WASM module as just a byte array. And then this byte array is something that's produced by Wasmer. So Wasmer allows me to run all the initialization steps ahead of time so I don't have to run it on every single row. Now this is really important because this code here in the UDF gets run on every single row. And if I have a million rows, I can't be doing some like initialization code every single time. This needs to be relatively fast. So I just load the bytes as a module, and then all I do is I call get function and apply to whatever the content of my row is. And that's it. Spark takes it. So now we're going to, hopefully, if the demo gods are on my side, see a live demo of it working. So this is what the front end looks like. The way I envisioned it is that you just select a file. So here's a demo file that I have, and it loads up the schema. And all you have to do is write a function in C that takes however many arguments you want and returns something of some type. So the example here, super simple, is just add, where it adds two numbers. So all you have to do is pick like two integers. So we can do the ID, which is just increasing, and then the balance, which is a large number. And then all I have to do is say, hey, for this WebAssembly module that I'm creating, the function that I want to call is called add. And then I have to just remind it that the output type is actually an integer. So then if I hit execute, all it's doing is it's uploading this little bit of code, compiles it as a WebAssembly module, and then right now it's running on my like little CSIL server, and we're polling for a result, and probably within the next few seconds, there we go, we have the result. So we have, all we did here was take the sum of this column and this column, which is, you know, pretty simple. But if you can imagine, you could write any arbitrary code here to do anything. Like you could call it to libraries, and also there's no reason why the code here has to be something that's just written in this little web UI. Like you could also just upload your own WebAssembly module that you've compiled yourself, and I can safely run it because Wasmer provides like a super lightweight VM for me to use. So yeah, that's it. Happy to take any questions or also a line of code to see if that works. The address of A? I have absolutely no idea. But the way that the addresses in WebAssembly work is like completely isolated from like the actual machine. So I'm sure it's going to be like, I'd expect it to be like a very low. Well, could you even get an address of this if it's just like it's just a primitive, right? So, it might just refuse to compile. But let's see. Can see if we get. Yeah. So if it complains about anything, it'll show up here. This is the output from Spark. Seems like a relatively happy output. Not sure what that means, but something. And it didn't crash, so that's good. So like what? Mm-hmm. Oh yeah, so that's a good question. So that's like basically something that the reason you would use WebAssembly. So I don't have access to any of like the normal like system calls that you would have access to, like if you were just running it on a Linux machine. And actually, the runtime environment, so in this case, Wasmer, has to provide implementations for everything. So if you try to like read a file or make a network call, it's just not gonna, it's gonna throw an error at runtime because that function doesn't exist. And if I wanted to theoretically provide that, I would have to like implement my own thing. So I could say like, oh yeah, I want to allow my user to like run very specific network calls, but by default, it's like all completely boxed off. Back there? I'm not sure. So like, basically, I feel like all the content that I read from like Wasm and the WebAssembly people have convinced me enough that like what they are doing is actually work. Like if I were to try to call any syscalls, it just doesn't expose any syscalls. It's not possible to do system calls from something running in WebAssembly. That's sort of like the design of the virtual machine. But I mean, if somebody can find a vulnerability in a WebAssembly VM, I guess technically I'd be vulnerable to that. Yeah, that's sort of like a make or break. So I'm probably going to try running some of that now to see how that goes. I don't know exactly what the performance penalty is, unfortunately. I think that's like kind of the big question here. Like this would not be useful if there's a high overhead, but my understanding is with WebAssembly itself, there's incredibly low overhead. You would expect like near native performance. So the question is like, is there overhead that's created by like how I'm calling to Wasmer? And are there maybe ways I can reduce the overhead? I'm not sure, but yeah, stay tuned. Yeah, so the time it would take for what the alternative that exists in the wild, this is like would already be probably a huge improvement, but the question is maybe that 40-minute time is worth it if the WASM implementation would be so much slower on like a 10 million row data set, right? Because this would be a variable cost and speed.
All right, so I think that's all the projects we have for you guys. Thanks for coming, even though this is not on the final exam at all. But see you guys in the final exam. Fill out the subject email. And